in the part 2 of this exercise, we're going to analyze a protein, which is a small protein ubiquitin. And in the following, this protein can be produced in different ways and even purified directly from the biological tissues. However, this specific material was overexpressed using bacterial cultures. So please watch the following segment showing the nature of this protein and resonance, location, and assignment.
Uniform 15N labeling is the simplest and the cheapest form of labeling. The protein is produced by expression from bacteria, which are grown on minimal medium supplemented with nitrogen-15 enriched ammonium chloride and wild-type glucose. It is a cheap and routinely affordable form of labeling which can be used for analysis of protein stability, interactions with ligands, and studies of protein dynamics. Here, 76 residues protein ubiquitin structure is shown with 15N atoms highlighted in blue. Uniform 15N labeling introduces large J coupling of 92 Hz between nitrogen-15 and directly attached proton. The first step in the NMR structural analysis is the quantification of the protein concentration using 1H1D overview spectrum. Since the proteins are usually studied in aqueous buffers, the strong resonance at 4.8 ppm stemming from 2 water protons has to be suppressed by application of a weak rectangular pulse with excitation bandwidth of 100 Hz on resonance with the water signal before the 90-degree broadband excitation pulse and FID acquisition. For protein quantification purposes, the acquired 1H1D overview spectrum has to be carefully phased and baseline corrected. After suppression with a weak rectangular pulse, preceding 90-degree excitation pulse, the water signal intensity at 4.8 ppm is comparable with the rest of the resonances in the spectrum. The chemical shifts in the spectrums are referenced relative to the signal of DSS at 0 ppm. The backbone and side chain aramide protons are resonating in the range of 7 to 14 ppm as indicated by the red arrow. The corresponding chemical groups are highlighted in the IL-44 to Fe45 fragment of ubiquitin in the insert. The aromatic protons are found in between 5.5 and 7.5 ppm, shown by the green arrow. They may partially overlap with the resonances stemming from aramide protons. Aliphatic protons span the whole spectrum from about 5.5 ppm to -2 ppm, indicated by blue, yellow, and purple arrows. This broad region can be further subdivided for regions populated by H-alpha, H-beta, and methyl group proton resonances.
Let's process 1D proton spectrum of ubiquitin and quantify its concentration. So we open our datasets, which we linked before, and here it is ubiquitin, so 1D spectrum of it. So we need to start from processing of the spectrum, phasing it, baseline correcting, integration, and analysis. So first, we define the window multiplication. And for small molecules, we used exponential window with relatively low broadening. For the protein, where the lines are significantly broader, so we have to use, let's say, squared sign, weighting function with the bell shifts parameter of 2. That's typical settings for the protein. So that should follow by Fourier transform. So we do Fourier transform. So here we are. And here we need to phase correct it. So usually for the protein it's done manually. So first of all we define the pivot point. So I prefer setting pivot on the right side and start with the corrections. So here we are, we're looking only at that part. So the signals should be phased on that part, so where the pivot is, so I just adjust it a little bit. So you can see the water signal, which is a dominant signal in the spectrum, is out of phase, but we still can correct it back using linear phase correction, but we're looking at those amide resonances. So now we're moving correction more and more until we get satisfactory correction of phases across all the spectrum. So these lines should be in pure absorption mode, and these lines should be also in pure absorption mode, so it looks good. So I save it. So zoom again. Now I can move the spectrum in the middle using these navigation buttons, and now I proceed with the baseline correction. So I again use manual baseline correction. So first I linearly shift it like this, then I adjust the whole spectrum in steps, so like in parts. So this is going to be my first part in here. So I lean it a little bit back. So here there's a baseline correctly represented, and here as well. So I delta it like this and save it. So you can see this part which I selected is baseline corrected, but this one is not. So therefore I select again full this part which has not been corrected and use baseline correction again. So now I can move it. First I will align it with the left side, and then you can see it's just a bit ahead, so I lift it up. So now my baseline is adequately represent the noise floor. So I delta it and save. Okay, so here is my spectrum. As you can see, I corrected it in two bands, band 1, band 2. Yeah, because the baseline was wiggling a little bit here, so I cannot use just smoothly declining or inclining baseline. So now I have to chemical shift reference it, and that is a little signal is my DSS. Here it is, 0 ppm. So I go to the calibrate axis, manual axis calibration. So I click here on the line, and then it says what is the frequency here. In DSS it's a 0 ppm. So I put it to 0 here. Yep. So now this is my spectrum is now fully calibrated, and now I can determine concentration by integration. So let me zoom here, and this is my DSS 5 micromolar concentration of it, so containing 9 protons, and this is methyl group, so one of the most shifted methyl groups, and it's another one. So I can integrate this peak and compare integral with this peak, and that will give me concentration of the ubiquitin. So let's do it. We go to the analyze and then integrate, and then manual integration, and so we choose the simple integration tab and integrate from here to here, relative integral of 1, and from here to here with the relative integral 3.1. Yeah, so I save it. So 6.1. So to calculate concentration of ubiquitin, we have to take into account that here there are 9 protons, here there are 3 protons, so 1:3 ratio, and the integral is 6 times more than that. So therefore 5 micromolar multiplied by 6 and divided by the ratio, that gives me the concentration. Alternatively, we can integrate this part of the spectrum, so up to here, which would include all the amide protons and aromatic protons. So let's integrate again. So manual integration, and now I can integrate from here to here. So that gives me this huge integral, and now we have to retrieve the sequence of ubiquitin, amino acid sequence of ubiquitin, and count the number of protons. So again, there should be aromatic protons and amide protons. So they all resonate here. That's a straightforward task, but it requires some analysis of the protein sequence.